Okay, so I just don't think you can separate being normal from deviation, which is why I wanted to go into that discussion about, deviation and dispersion, because that all kind of gives us this foundation for what we kind of consider normal. In statistics, a normal curve is a data set which has a bell-shaped histogram. So, data set that has a bell-shaped histogram, bar graph for quantitative data. And so here's what I mean. When I look back to these classes, these exam scores, which one seems normal? This one. This one seems more normal than the other two. It is very abnormal to have everybody get the same score. And it is also abnormal to have half of everyone get a 50% and the other half get a 90. These are two very abnormal situations. But this is a little bit more normal, where most of the people score right around the same thing, a little bit above and a little bit below. This is more normal. And notice here, so when they say a data set that has a bell-shaped histogram, they're thinking a bell, right? Like, can I draw? Yeah? Like a bell? Right? There, yeah? Like ding ding. So, so they're thinking, okay, like this is the closest thing to bell-shaped. Definitely more than those, yeah? And so, so it got its name, this, when this happened, when the bar graph kind of you can imagine it being, or when the histogram, you can imagine being squeezed in the shape of a bell, then that's pretty normal. Most of this stuff is right around the average, and then there's a few in the extremes, in the lows and in the highs. Okay, so a few remarks about normal. The data set from this class, this is called uniform, this is called bimodal, this is called normal. Skewed is left out, so I'm going to just jot that down so that we have a reference to it. So we looked at uniform distribution. Distribution. A bimodal, and normal. And I'm going to put no skewed. We didn't see one that was skewed to the left, or skewed to the right, or skewed to the left, but you'll see that in the next class, sure. The mean, the median, and mode are all equal in a normal data set because they're right around that middle. It's pretty symmetrical. So the mean is equal to the median is equal to the mode for normal data sets. Okay. Another thing that's remarkable is the standard deviation. It's just a tool we use to measure the data spread. So standard deviation is a measuring tool. Okay, for spread. or deviation, if you will. Yeah, but the higher that measure, the more spread out it is, and the lower that measure, the less spread out the data is. And then my last remark here is that a z-score is a number that counts how many deviations a value is from the average or from the mean. So the z-score counts how many standard deviations a data value is away from the mean. Okay, so let's take a look at that. Let's look at the walking age. The average age when a child starts walking is 15 months old with a standard deviation of 3 months. So we're thinking the average is 15, the standard deviation is 3 months. A child is 21 months old. How many deviations is that child away from the mean? Well, 15 plus 1 deviation, that would make 18. Plus another 3, that would make, so 15, 16, 17, 18, 19, 20, 21. Two standard deviations away. So and the z-score counts how many standard deviations it is away from the mean. Okay, so that means the z is 2. Got it. So maybe I'll just write that. 2 full deviations away or above the average age. A child is 12 months old and they start walking. How many deviations is this child away from the mean? Well, 15 take away 3 makes 12. So how many deviations? They are 1, but 1 below. So they are 1 deviation away from the mean. The average is 15. And so 1 of these below it. 1 below. 6 months old. Well, this super little cutie tiny half a year old. How many deviations is this child away from 15? Let's compute that. So minus 1 deviation would be 12. Minus another deviation, 12 take away 3 is 9. Minus another deviation, 9 take away 3 is 6. Okay, so how many deviations? 1, 2, 3. 3 below. 3 standard deviations below. So 3 sets of 3 below the average of 15. 22 years old, 24 months. How many deviations is this child away from 15? 15 plus 3 makes 18. 18 plus 3 makes 18, 19, 20, 21. 21 plus 3 makes 24. Okay. So how many deviations? Positive 3. 3 sets of 3 above. Okay, and now I always have a lot of students when they're working this out say, okay, well, let's do this. The difference between 15 and 21 is 6 months. So they will quite honestly compute the difference. And then they'll be like, okay, and so how many 3s are there in 6? Well, that's a division problem. There are 2 sets of 3 in 6. So they keep doing this. What's the difference between a 12-month-old and a 15-month-old? Well, 3 months. 12 minus 15 is -3. And how many 3's are in that? -3 divided by 3 equals -1. And how far apart is a 6-month-old from a 15-month-old? Well, 6 take away 15 is -9. How many sets of 3 are there in a debt of 9? Well, that's 3 sets of debt or whatever. I don't know. However you want to interpret that. Negative 9 divided by 3 is -3. And they do it similar, just not how I had done it, which is totally fine. How far away, or what's the difference between a 24-month-old and a 15-month-old? Well, the difference is 9 months. How many standard deviations, how many sets of 3 are there in 9? Well, there's 3. Okay, so this blue stuff is just a completely different way of solving the same problem, but just wanted to show you that, other people do it a little different. That's totally fine. Maybe I'll alternate back and forth right now. A child is 15 months old. How many deviations is that from the average? Well, the average was a perfect 15. Okay, so just so that we remember, the mean was 15 months old with a standard deviation of 3 for walking age. So here, how many deviations? 0. It is right at the average. A child is 16.5 months old. Ooh, how many deviations? Well, not a complete one, because 15 plus 3 makes 18. 15 plus 3 makes 18. That's too much. 15 plus 0 makes 15. So this is, but what's a half? A half of 3 is 1.5, and that would give us 16.5 months old. So how many deviations is this child? Well, half. A half of a deviation. Half of 3 was 1.5 months, and that's how far away, or how far apart this child is from the average age. Now if we did it the other student way, which I thought was fabulous, and so I'm going to write it down, then this would read, what, 16 minus 15, 16.5 minus 15 to find out that those are 1.5 apart, and then 1.5 divided by 3. Well, there's a half of a 3 in, so how many 3's are in 1.5? Well, half. Half of a 3 is 1.5. So we still end up with the right answer here. Maybe I'm just going to stick with this for a second here. Child is 10.5 months old. So how far away is that from 15? Well, glad you asked. So what is, we got -4.5? So more than one full one below, 1.5 below, I would say. So take this -4.5, divide it by how many sets of 3, and we get -1.5. So here, Z, how many deviations? 1.5 sets of 3 below. So when I'm thinking about it in terms of my logic, 15 take away 3 makes 12. 12 take away another 1.5. That makes 10.5. So 1 complete 1.5 of a standard deviation. Ooh, if a child is X months old, how many deviations are they? Well, this, ooh. Well, okay, if we look at it purple style, It's almost like something like this would read 15 plus 1, 2, 3, 3 sets of 3 equals 24. And this one would read 15 plus 2 sets of 3 equals 21. Okay, and so if I'm going to extend this and kind of put in a generalization here, the 15 is the mean. The 2 is playing the role of z, how many. The 3 is the standard deviation. And the 21 is our data value. Does that fit here? Does that fit the mold? The mean plus the z is 3. Okay, also the standard deviation is 3. And that equals the child's age. So here the x is the child's age. Okay. Or we could go blue style. And blue style, okay, so let's generalize that. Blue would be the child's age. So take the child's age, subtract the mean, then take that and take that whole amount and divide it by the standard deviation, and that will spit out the number of standard deviations you are away from the mean. Ooh. Okay, so I see two different things that people could write here. Either you could use this logic, this purple logic, and you would come up with this pattern. The mean plus z times the standard deviation equals the age of the child. Or you could take the age of the child, take away the 15 to find the difference, and then divide by the standard deviation to find out how many times does that go into it. And that will give you the number of deviations away this child is from the mean. So I see two different formulas we could write here. What did we write? We wrote the mean plus however many standard deviations away is going to give you some value, or like the age. Or did we do? We did the age, take away the average, and divide that by the standard deviation, and that will give you how many? So just so that we're keeping tabs on this thing, right? This would look like x minus 15, and then divide that by 3. And this one, viewed a little bit differently, would be, okay, take the mean. So the 15 plus however many 3's, and that should give you the age. Yeah? So either way, either you're solving this equation, which is purple style, or you're looking at it like this and finding the difference and then counting how many standard deviations were there. So could look at it either way here. If a child has a z-score of 1.7, what can you say about the kid? Okay, no, so now we have the z, and we're working backwards. Okay, we can do that. I think I'm going to look at the purple one, just because it seems easier to just put in a 1.7 here in order to figure out the child's age. So, looking at this purple style, the kid's age is 15 months plus 1.7 standard deviations, which is 3, away from the mean. Okay, so 15 plus 1.7 3's. Is 20.1 months old. Not to be confused with 20 month and a day. This is 1/10 of a month. Anyway, right around 20 months old, just over 20 months old. If a child has a Z of negative 2.2, what can we say about the kid? Well, kid's age is okay. Well, take the average and take away 2.2 standard deviations. 15 minus 2.23s. 8, almost 8.5 months old. Okay, that's what we can say about the kid. Well, that kid's about 8.5 month old. So Z-score, we're just going to write down that it's a formula. The Z-score is equal to, okay, that. I feel like that is the easiest way. It's already solved for Z. And so let's write that down. And in terms of what it means, it is the number of standard deviations away from the mean. So Z-score is equal to, here it was the age, the difference between the age and the average age, and find out how many standard deviations go into that. So the Z-score is the difference between the age and how many, and then counting up how many standard deviations that was. And that's because this equals the number of standard deviations away from the mean. Okay, so in summary, I would like to look back to the to how we started. We had talked about the fact that in section 2.7 is really talking about normal. And in order to talk about normal, I really think you have to talk about deviation and Z-scores. So then we started talking about dispersion and standard deviation to talk about how spread out the data is, because then you can start talking about the fact that this one is a more normal situation and these are a little bit less normal. And the dispersion, the range, and the standard deviation give us some measurements for that type of thing, but they don't really give us a measurement for like the picture. However, we also use those to think about consistency, right? If that standard deviation is really talking about these class averages or golfers or things of that sort, then we can start to think about, okay, who's more consistent or which class is more consistent. And then after we think about that, we can think, okay, after we talk about consistency, then what's normal? What do we consider normal? And so then we can start talking about, well, we think that, you know, the walking age of kids is pretty normal. Normally they walk around 15 months old, okay? And the deviation of that's about 3 months, you know, like, it's not super spread out. It's pretty close to this, because once you spread out further than that, then you've got a really young kid, or like you have a 2-year-old who can't walk yet. So in the end, when we're going to talk about normal curves, which we're going to finish 2.7 talking about those normal curves and what's normal, we really also need to talk about how does it deviate and how does the spread look. So that's what we did.